Good afternoon, everybody. So, as in continuing with the last class where we left, I think we stopped at the experimental designs. I think the presentation was okay with you had the idea of what is an experimental design, what is a design through the last presentation. I think in continuing with that, that is experiments, design of experiments. I will take the second class, in which I will just elaborate you about what is actually experimental design, how to analyze. As already I told you in the previous class, this design of experiments includes one part is conduct of experiment, second part is analysis of variance. Okay, so in continuing with that, so we'll just elaborate one more time some of the points which I did not cover in the first class. Okay, some of the items, so that you can have the complete idea of what is an experimental design and further analysis, right? Okay, right now you can just have a look at the slide wherein we have got things like experiment, design of experiment, response variable, experimental unit, factors, level and treatment. These are the 5 or 6 items that have been mentioned in the slide. Okay, so if you just look at the first point, experiment means the process of collecting sample data. Okay, process of collecting sample data with respect to the statistics. Okay, actual experiment can be in any of the disciplines. It can be in clinical trials, it can be nutritional trials, it can be an extension study, it can be a survey, okay, it can be a microbiological work, anything wherever data is generated. So experiment depends on the discipline or area in which it is conducted. So naturally, being part of the statistics, we are dealing with only the process of collecting data and analysis of data. Okay, so that is the experiment, process of collecting sample data with respect to statistics. Okay, so then design of experiments. So design of experiments is a plan for collecting the samples. So how do you collect the data? So we'll just elaborate what are the designs available, okay, one by one. Then we have got response variable. So this is third item, it's an important this one there. So you can just see the third item is the response variable. Okay, you can see it is an response variable. Okay, response variable means, so as already I just told you, just to mention a example. So you can say take milk production as an variable. Okay, milk production can be taken as a variable. Okay, so here, so we have denoted it by the letter Y. We have denoted that by the letter Y. Milk production is, in the example, we have taken it as Y. So naturally, whenever we conduct experiments, there will be a variable. Invariably, variable is compulsory, must. Milk production, body weight, something to record, some character to record. So that will be a response variable. Okay. Then the fourth point is you have got experimental unit. Fourth point is experimental unit. So experimental unit here in this example, to continue with the same example, so I told milk production is the variable, experimental unit will be a dairy animal, either Jersey crossbreds, HF crossbreds, Malnad Gidda, okay, any examples, Hardika, Ramrutmal, any lactating mother, or buffalo also. Buffalo will also be can be experimental unit depending on the availability. Then we have got the next point is factors. So this says factors are nothing but independent variables. So now I mentioned as third point, I mentioned as response variable. Okay, so responsive variable is influenced by the independent variables. Those are factors. Okay, those are the factors. Okay, so these factors have got a influence over the response variable. Okay, so for the example of milk production, I gave experimental units are dairy animals, and factors will be the lactation number, okay, nutritional status of the animal, breed of the animal, like this. Few examples, few independent variables that influence the milk production are these, like breed, lactation, nutritional status. Few examples. You can take many variables also, many factors which will be influencing the milk production in an animal. Okay, so we are giving only few examples there. So like that, there will be many factors there. So then we have the levels. So levels means each factor, influencing factor, can be divided into different levels. This will only come in the factorial designs that we'll talk about when we come to the design levels. Okay. So factors and levels are within this one independent variables. Okay. Then we have got the other thing, treatment also. These last three factors will be a part of the independent variables whose influence is tested on the response variable. Okay. So treatment actually is combination when we have two or more characters to ascertain or determine their effect on the response variable, then we call it as treatment. Although treatment is generally given a name given for the independent variables which we need to test. It can be combination also. So as it is mentioned here, you can just read that sentence there. A particular combination of levels of the factors in an experiment. Okay, that is a level of, we'll say with the example, one of the example, for example, feed and breed. If you have feed as well as breed to be tested in an experiment, if there is an interaction between these two, that is feed and breed, so then that combination will become the treatment. Okay, specifically that combination becomes the treatment. So although generally we take feed as an independent treatment and breed as an independent treatment, technically sometimes treatment is referred for the combination of two factors. Okay, I think that is clear there. We will just move on to the next content. So I think the important principles of experimental designs have been explained to you through the things are important feature principles are replication, randomization and blocking. Okay, any experimental design must have these features or these principles. It should be based on these three principles. One is replication. I have told you what is replication. Okay, replication, randomization and blocking are must for the experimental designs. So although in some of the designs only one or two of them are applied, in some designs all the three are applied. Okay, so in the example, randomization is an important this one, and the important objective of the experimental design is to identify the effect of, we'll come back to the previous slide. Okay, is important objective of the experimental design is to determine the effect of last three factors, that is factors, levels and treatments on the response variable, and see whether this influence of these factors, levels or treatments is due to chance or not due to chance on the response variable. For example, whether in the same example, to continue with the same example, whether milk production is the difference in the milk production between animals is influenced by the breed or feed or by the nutritional status. If the influence, is it due to chance or just due to the exactly feed level, feed or breed. Okay, significance, we are trying through the experimental designs, we are trying to ascertain the significance of difference. Okay, ascertain the significance of difference or the randomness of the difference. Okay, you just note down this point. We are trying through the experimental design, we are trying to ascertain whether the observed difference or visible difference is due to significance or due to chance factors. Okay, you just note down this point. The important objective of the experimental design is to ascertain the significance or randomness of difference between the production levels or the random variables. Okay, is to ascertain that factor. So that is being achieved through. So for that reason, we need to randomize the experiment. So randomize the experiment. Randomization, I will just put a one sentence there because already it is told. Randomization, as already told, it is to see that biasedness with respect to variation among the experimental units is removed to the extent possible, so that the factors or treatments we are testing are genuinely tested or analyzed. Okay, genuinely tested or analyzed. In order to do that, we are randomizing the experiments. So a randomization means if you have a group of experimental units, homogeneous experimental units, you should allot them equally to all the available treatments. That is the simplest meaning of randomization. Okay, then we how to randomize, that also occurred in the last class, either by the lottery method or flip of the coin method or using the random number table. You can, if the experimental units are exhaustive. If the experimental units are exhaustive in number, okay, then you can go for the random number table can be utilized. Okay, random number table can be utilized. If the number is less, you can just go through the lottery method. Okay, you can just go through the lottery or flip of the coin method. If again further, if it is a very extensive, you can use the statistical software packages or programs. Even Excel program, MS Office Excel can also be utilized, or other programs can be utilized to allot the experimental units randomly in the experimental design. Okay, then we'll just come exactly to the what is actually a statistical model. There will be a statistical model in each of the experimental designs. Okay, in any experimental design for that matter, we have got few. So in any experimental designs, we'll have a variable. As already told in the first slide, we'll have a variable. Examples are body weight, milk production. Okay, or it can be, if you go to microbiology, it can be colony forming units, whatever. So whatever that varies with the individuals is referred as a variable. Okay, it will have the variable and influencing factors in the form of independent characters, and there will always be some amount of error. Small amount, small or large, there will be some error in any of the experimental designs. Okay, so these are the basic these ones. So once we have this, so in the model what we try to explain is, we say how this variable first point, okay, how this variable first point is being influenced by the influencing factors, independent factors. Okay, so that is, and how it is, for example, if the milk production is something like 10 liters, if this 10 liter is being influenced by breed, age, okay, lactation, like that. Okay, it will be influenced by these factors. So how to assess them? It is done through the statistical model. So if you just want to repeat that, if I want to put it in the form of the equations, it can be put in the form of equations also. Okay, that is 10 liters of milk production is influenced by, so there it will be y is equal to mu. First one is mu plus the factors, other factors like, as just now I told you, breed is one of the factors, age can also be another factor, plus other factors and exception. All after including all the variables, we will have the errors also. Okay, we will have the errors also as the important fact value in the this one model. Okay, that model basically is nothing but an equation that defines the influence of different factors along with the error on a response variable. Okay, right, I think that is sufficient with respect to the statistical models. I think then what we do in the exactly in the experimental designs is, once we have the data, it will be subjected to what is called a technique called as variance partitioning. Okay, variance partitioning. Okay, so that is called as analysis of variance. Okay, then we have, unlike, I will just also tell you one more thing here, important thing. As I introduced this experimental design, we told it is can be a test of significance or hypothesis testing. Okay, the only difference, if you have solved the problems already in the practicals, you will observe that there we have one sample, one population mean, or two samples, okay, or two sample proportions, like that. Okay, then if you come to the experimental designs, we'll have one important, this one is number of samples. Okay, number of samples are more, or treatment combinations are minimum more than 2, 3 or more than 3 samples or treatment combinations will be there in the experimental designs and analysis of variance. Okay, so unlike one sample, one population, or two samples in the previous test like T, Z and other things, and in chi-square we had some groups were there, some categories were there where the data was qualitative in nature, that is number, data in the form of number was there. Okay, here in the analysis of variance, we will have the 3 treatment combinations or 3 or more samples will be there. Okay, that is the important difference. Then at a time you are testing all the samples, available samples. Then most of the time, or all the time, you should say, the analysis of variance involves a quantitative variable. Okay, analysis of variance involves a quantitative variable. Okay, it will involve a quantitative variable, like just now I told you milk production, body weight. Okay, anything that is measured on the scales, that is called as a quantitative variable. So you will have a quantitative variable to for the design of experiment, for the experimental designs. Okay, then we'll just move on to the designs specifically. What kind of designs are there, available designs? Okay, basically as we already told you in the first class, design is a plan to obtain the data we require and subject it to analysis. Okay, so in that we have got, first one is completely randomized design. A first design is completely randomized design, also called as CRD. Okay, it is simplest of all the designs. It is a very simple one. So only thing what we require here is group of homogeneous animals or experimental units. Animals I am saying with respect to the respect. If you go to the other areas, it can be things, it can also be things. Either things or animals or individual human beings can also be the experimental units. So we need a group of homogeneous animals. Why we say homogeneous? Because we would like to see the effect of independent variables on these experimental units or through the response variable. Okay, through the response variable. For that reason we need the homogeneous group of animals. If we have group of homogeneous animals, sufficient homogeneous animals are available, experimental units are available, you can go for right away go for the completely randomized design. And there will be usually only one kind of character that can be tested, one kind of independent variable that can be tested. That is the two important things. One is we need to have group of homogeneous animals. The best example homogeneous animal, when we say homogeneous group, hybrids. Okay, hybrid broilers, hybrid layers, will get sufficient number of hybrid broilers. Or you can also say take lambs belonging to a particular breed. Okay, so usually larger the animals, difficult is the conduct of experiment because it involves huge cost, and at the same time it will also, we cannot have large number of sample size cannot be done, cannot be subjected for experiment. For that reason, so if there is importance is there, you can do experiments with the large animals also, but with restriction of sample size. Okay, then we have replications of treatments. What is there? Actually we can just see there, and the first bullet is replications of treatments are assigned completely at random to independent experimental subjects. Okay, as the name says here, completely randomized design is we have group of experimental animals or experimental units, and at the in the other way we have got other side, we have got the treatments or the factors which need to be tested. Okay, like feed, okay, or breed, or you can also have the lactation number, anything can be there. So there will be only one set of or one kind of treatments characters. Okay, you cannot have two sets of characters. We cannot test breed and feed in the completely randomized design. Okay, we can either test breed or feed or the lactation number, like this. So we will have only one set of, so within that we can have any number of levels. That is, you can have breed 1 to breed 5 or breed 6 or breed 7. You can have feed number 1 to feed number 7, like this. Okay, you can have any number of, okay, you can have any number of independent factors in the breed we can have, okay, in the breed we can have Malnad Gidda. Okay, then we can have the Jersey crossbred, like that. Within the breed we can have any number of breeds, or you can have Hallikar, like this. You can have any number of varieties or levels within that. Or you can also have, if you take the example of feed, we can have feed as one important independent variable. Within that we can have feed 1, okay, we can have feed 1, feed 2, feed 3, like this. Okay, you can have any kind within a particular independent variable. Understood? I think that is better there. Now we will just go on to the what else will have. Only then the point is they should be randomly, all available experimental units should be randomly allocated to the available experimental treatments. Okay, if you have 30 and 5 feed groups are there, 6 animals should be randomly allotted to the each of the treatment available. Completely randomized meaning is each of these 30 have got equal chance of being selected to the any of the 5 feed category you have got. That is the meaning, completely randomized design. So it is a simple design, and we have, then you can have the, that is you can, if you, when you solve some of the problems in the practicals, you will come to know what is the design. And for this completely randomized design, the statistical model will be mu, mean is equal to, okay, sorry, y is equal to mu plus one important factor. Which is that important factor? We have got either you can test feed or breed plus error, okay, plus error. Okay, we'll have only these as the model for completely randomized design will be dependent character, that is y is equal to mu, that is mu is population mean, then the effect of feed or breed or anything, any of the factors plus error. So this will be the model for the completely randomized design. And usually the data obtained from completely randomized design will be subjected to one-way analysis of variance. Okay, will be subjected to one-way ANOVA. Okay, will be subjected to one-way ANOVA, right? So we'll say what is that one-way ANOVA when we just come to the practicals. You can just understand what is that one-way ANOVA, right? Okay, with that we'll just move on to the next design, I think, and we'll have, you can have any number of this one. We'll just move on to the next slide there. So complete, just meaning again it is elaborated here. Okay, we have got sample layout. We have got, for example, if we have A to D treatments, or we are giving only general picture of this, and you can just obtain the meaning of that. Okay, so we have 3 replications, that is 3 animals for each treatment. So we have got basically so many, that is 12 replications are required, 4 into 3. So they have been allotted here. So here actually we have got, you can just see there among the 12 animals. So each treatment will have 3 replications. Okay, each treatment will have 3 replications. You can just count that. Okay, for example, A has got A1, A2. Okay, somewhere A3 is there. So basically each treatment has got 3 replications, that is been explained here, right? So if you just look at the, and in the place of what we have shown here is, we have shown you the experimental units, that is A1, B1, C1, A2 is there. So along, this is the design, this is basically a design. So when you complete the experiment, what we'll have in the place of this, we'll have the values corresponding. For example, when A treatment is given for replication number 1, there will be response variable, there will be 12 sets of values. Okay, there will be 12 variables like milk production 5 liters, 6 liters, 7, okay, 8, 9, 10, 11, like this. There will be 12 variables, 12 numbers will be there, 12 values will be there in the form of the data input format, right? So we'll have, so we'll just see that, you can just see that later on when we go to the practicals. In the practicals you can just understand what is that. Okay, so by at this point it is only completely randomized, means available homogeneous group of animals are randomly allocated to the available number of treatments. We should see that each treatment gets as far as possible equal number of replications, and each treatment should get equal number of replications. That is the minimum, this one. And the first and foremost thing is there should be randomization. Okay, there should be randomization. Okay, then we'll just move on to the other design, other important design called as randomized complete block design. Okay, randomized complete block design. Okay, randomized complete block design means, so randomized, as the name says, randomization is the compulsory, this one, complete block. So here we'll have the one important difference is, we will have one more source of variation, one more source of independent variation to be tested along with one set. In the CRD, I told only one set, that is in the, either in the form of breed or feed. I told it is either breed or feed will be there in the, or anything will be the, any one of the character will be there in the completely randomized design. So when we come to the RCBD, we have got the option of including one more independent variable. Okay, so there will be response variable or dependent variable will always be there in the form of y. Okay, y, a character that needs to be subjected for analysis, will always be there. Along with that, there will be one factor that is in the form of breed or feed will be there, and another factor which is already proven to be, that is this factor will come only when, as I told you already in the CRD, we need to have homogeneous group of animals. When we don't have homogeneous group of animals, then we have got the randomized complete block design. Because I think as in the first class I told you, getting large number of homogeneous animals, especially in the livestock, will be a very difficult task. So for that reason, you can have even in the agricultural experiments also. So in order to remove the variation and improve the accuracy of analysis, we adopt the RCBD, randomized complete block design. What we do here is, for example, I think I told you age and lactation numbers is an important factor that influence the age and lactation, or the important factors that influence the milk production. Okay, when we know that it is fixed, age does have got the influence, lactation number also has got the influence on milk production. When we know that, we can bifurcate that variation, we can take away that part of the variation from the experiment or keep it aside, so that we'll have the better accuracy of experimentation. So that is done through blocking. So that is, we create blocks for the existing or proven source of variation. For example, when we have lactation number of, all the 30 animals are not available, you have animals belonging to different lactation. In each of the treatment, that is feed category, you can put animals belonging to lactation number 1, lactation number 2, lactation number 3. Okay, so that what it does is, it removes the variation attributed to lactation or age that is already known to us from the overall variation, so that you will have the accuracy, increased accuracy of the experimentation will be better. Okay, that you will understand when we come to the problem section little bit. I think it will be clearer there. Okay, we will just move on to that is the randomized complete block design. So difference is, as of now, it is here, it will be, and the design for the model, statistical model for the this one, your RCBD will be y is equal to y, that is dependent variable, is equal to mu plus, mu is the population mean, plus the one factor is treatment factors. Okay, one factor is treatment factor plus the effect of blocks, plus the effect of blocks, plus along with that there will be error also. Okay, there will be error also. So addition is, what is the addition compared to CRD? We had y there, mu was there, treatment was there. In along with that, there will be the effect of blocks also there in the blocks is also there in the RCBD. Okay, that is the difference. Okay, and most of the time and all the time, RCBD data will be subjected to what is called as two-way analysis of variance. Okay, it is subjected to a technique called as two-way analysis of variance. Two-way analysis of variance, right? With that, I think that is about the RCBD. And now we'll see, just see how this whole this one happens and other things. We'll just see here. You can just okay, so other things about the randomized complete block designs are, you can just, I will just read out that, you can just see that there treatments are assigned at random within the blocks. So I told you, lactation number 1, if you have 4 lactation animals are there, in each treatment you allocate the animals belonging to each lactation. That is the meaning. Treatments are assigned at random within blocks. Okay, within blocks of the adjacent subject, each treatment once per block. Okay, so this you will understand. We are given some simple problems are given in the practical manual while solving them. So although we are not given actual elaborate problems are not given, very simple problems are given. While solving the problems, you will come to know what is this RCBD all about. Okay, so at this point I can also say, usually what we have given is RCBD without replication we have given for the manual. Okay, without replication means for one block, for one treatment, only one experimental unit is the RCBD without replication. If we have more number of replications per treatment per block, that will be RCBD with replications. Okay, so let us not bother about that. We have RCBD without replications only. Then the second point is, the number of blocks is the number of replications. So because as I just now told you, we are allocating only one replication per block. For that reason, number of blocks will be number of replication itself per treatment. Okay, any treatment can be adjacent to any other treatment, but not the same treatment within the block. So this will understand. I'll show you one of the layout there, used to control the variation in an experiment by accounting for spatial effects. These spatial effects, especially agricultural experiments where plots will have different kind of fertility. In order to take care of that, the whole plot is divided into whole sowing area is divided into different plots, and analysis is done for plots independently. Okay, that just we'll see one of the design. We will just, you can just have a look at this simple layout that has been given here. We have got each horizontal row represents a block. Okay, block 1, block 2, block 3. You can just see that, right? Block 1, block 2, block 1, block 2, block 3, block 4, and we have got 4 treatments. Okay, so in each block you can see there is at least one time the treatment has come. In each of the block, the treatment is repeated at least once. So for that reason, so number of replications per treatment will be number of blocks itself. Okay, so number of replications per treatment will be number of blocks available itself. So as we just pointed out in the previous slide. Okay, so in the actual experiment, this is the experimental design. In the actual experiment, what we have is the values. You will have the values. Okay, numerical values will be there. In the place of A, one value. In the place of B, one more value. In the place of C, one more value. In the D place also one more value. Like that, it will be repetition for the remaining 12 replications also. So instead of this is the design. Okay, this is the design. So once you conduct the experiment, what we'll have is set of 16 values. You'll have the set of 16 values will be there. Okay, so these will be subjected to analysis of variance, right? So we'll just go on to the next slide. Let us just see what is there. Okay, so we can just see. So the another third kind of designs are factorial designs. So for all your reasons, we are only taking only Latin square design is being explained to you. So will be explained to you. So in that one, the only change is factorial. So I told you in the designs statistical model. So there is gradually there is an increase in the source of variation, right? In the first this one we told, in the first CRD we told mu is equal to y is equal to mu. It is there in all the designs. Okay, and when we along with that, error is also common. Okay, error is also common in all the designs. When we come to the CRD, we had one additional source was there. For that reason, one source of known source of variation was there. When we come to the RCPD, there will be 2 more sources of variation along with these 2. Okay, along with mu and error, there will be one more source of variation in the CRD, and when we come to the RCPD, there will be the increase. That is one more source of variation in the form of blocks. Okay, in the form of blocks. The variation due to blocks, variation due to treatments is the increase. This one. Okay, that is the difference. So when we come to the factorial designs, what happens is we will have, in addition to mu plus error, mu is nothing but population mean, that is influence of the population mean. Okay, influence of the population mean. Along with that, error will be always there. Along with that, instead of 2, there will be more than 2. 3 or more factors, 3 or more known sources of variation will be there in the statistical model. Okay, the one important difference is when we say factorial designs, there will be increase in the number of source of variations. Okay, and usually factorial design accommodates more complicated things to be tested, more number to be tested in the same design. Although it is very efficient, but analysis wise it is a complex design. Okay, so careful selection, you can I'll just read out whatever is available in the slide. Careful selection of combinations of factor levels in the experiment, as I just now told you, will accommodate more number of sources of variation to be tested. Provide information on factor interaction also. Okay, it will have the regression model includes main effects, So two-way interaction, three-way interaction, just now, as I just now explained you, there can be interaction among the different factors also. For example, I told you breed and feed factor. Let us say feed and lactococcus. Okay, we want to test feed as well as lactococcus. Okay, we want to test the feed as well as lactococcus, or lactococcus means galactococcus, those supplements which improve the milk production. If you want to both test both of these, that is milk boosters, let us say milk boosters, so we can include these in the analysis, and we can also study the interaction between feed and milk booster also. That is the combination that needs to be tested. So as just now I told you, this analysis, as we increase the number of factors to be tested for their effect on the significance, the design becomes little more complex. Okay, little more complex. Okay, what is that complexity? We'll just see. So basically, we'll come to the second part. I just introduced you what will be the second part when I said values and other things. So basically, when we conduct the experiment, we'll get the data. Okay. So once we have this data, it will be subjected to what is called as analysis of variance. Okay, it will be subjected to a technique called as analysis of variance. What is done in analysis of variance? Partitioning of the variance according to the model. So this I have explained you already. Okay, partitioning of the variance according to the model. According to the model, when I say, so I said the factors like mu and error, don't worry about those two. Okay, mu and error, we are not considering. Other two factors in between, that is your treatment factors, okay, or breed factor, okay, or feed factor. These will become, or even generalized blocks factor will become the sources of variation. So what is that includes? We'll just see here. Okay, what this ANOVA includes, what it contains basically. What it contains is basically the source of variation. Okay, it includes the source of variation in the form of, okay, in the form of breed, treatment, or error also. Okay, or error also. Error will also be there in the source of variation. As I already told you, you cannot remove in the error portion in any kind of accurate experiment. Error will always be there. Only thing is there should be reduction. The extent of error should be minimized to the extent of possible. So there will be source of variation, there will be degrees of freedom, there will be, it is almost a calculation part. Okay, it's almost a calculation part only. So we will have the source of variation, we will have the degrees of freedom, we will have sum of squares, we will have mean sum of squares, and you will have ultimately at the end, as the end product of analysis of variance, you will have the f value. You will have the f value. So this f value is nothing but, this f is nothing but, it is mean sum of squares, okay, mean sum of squares between treatments divided by error mean sum of squares. Okay, error mean sum of squares. So that will be the f value. So what you basically do is, so as part of the test of significance, you will have the, once we do this ANOVA and other things, okay, once we do ANOVA and all, you will have a f value, and we will just see, the next, this one is designs analysis, what we do exactly in the analysis. So I have to explain to you what is ANOVA. Okay, so what we do in design analysis and interpretation is, as usual in the test of significance or test of hypothesis, you will form the null hypothesis and alternate hypothesis. Okay, null hypothesis I have told you, hypothesis of no difference. So to begin with the experiment, you say there is no difference among the breeds with respect to milk production. Okay, so this could be my opinion. So I may say there is no difference between milk production potential of Hallikar and Amrut Mahal. Okay, that will become the null hypothesis. Okay, in the beginning of the experiment. Alternate hypothesis in that angle will be, there is a significant difference between milk production of Hallikar and Amrut Mahal. Okay, that is the statement. So then once you this is for that example, milk production. It can be different for different experiments. Okay, once you do the formation of null hypothesis, meanwhile you can just add one more point there, conduct of experiment before the ANOVA. Before the ANOVA, you will have the conduct of experiment also. Okay, you need to have the experiment also. Okay, once you form the hypothesis, you conduct the experiment. Okay, either CRD or RCBD or factorial, whatever design you conduct. So once you conduct that, you'll have the ANOVA. Next thing will be analysis of variance. So you'll subject the available data into analysis of variance. Then, as just now I told you, F value, end product of ANOVA will be F calculated value or F value. So you obtain this F calculated value, compare with the table value. Okay, so it is at a particular level of significance. Here also you can add one more point here. Another point is, what is test of significance? We are told we should also fix the level of significance, or 5% or the 1%. Okay, we should have the fixed level of significance also, right? So at a given level of significance and the for a given degrees of freedom, you will have the F value, calculated value also will be obtained, right? So you will compare these two, F calculated value and table value, and depending on them, you accept or reject the null hypothesis. Okay, accept means, when do you accept? When the F calculated value is less than the table value, you accept the null hypothesis. When it is more, you reject the null hypothesis. Okay, and it is always at a given level of significance. Okay, it is always at a given level of significance. 5%, most of the time common is 5%. Common level of significance is 5%. Okay, then on the basis of this same thing, on the basis of this last point, that is acceptation or rejection of null hypothesis, you will interpret the conducted experiment. I told in the beginning, there is no difference between milk production of Amrut Mahal and Hallikar cattle. Okay, so after the conduct of experiment, recording the milk production, taking the data, subjecting it for analysis of variance, calculating F value, accepting and rejecting. For example, if you accept the null hypothesis, what it says is, there is no significant difference, or you can indirectly, in the other way also you can say, to be specific, the observed difference between milk production potential of Hallikar and Amrut Mahal is not due to significance, or you can also say is due to chance factors, is due to chance factor. There is no point to worry about that, like that. Okay, so if it is rejected, you can say the observed difference between the milk production potential of Hallikar and Amrut Mahal is not due to chance factors, it is due to significance. You can say like that. Okay, so that is the meaning with respect to this analysis of variance and design of experiments. I think that is sufficient for your this one. I think only what I missed in the LSD is in the experimental designs is LSD, Latin square design. We will just add it up in the next class, any of the classes that will be taken. Okay, I think with that we will close the session.